Welcome to today's Explainer. Grab a seat at the bench, folks, because today we are stepping into the lab to build an AI chatbot from the ground up. We're going to peel back the curtain and see exactly why algorithmic efficiency isn't just some dry academic theory you memorize for a comp sci exam. No, it is actually a vital survival skill for your startup. We're going to see firsthand how the data structures you choose will literally dictate whether your next big idea soars or, well, completely crashes under its own weight.
All right, here's the syllabus for today's lab. We're covering the chatbot scaling problem, lists versus hash tables, TensorFlow and fast inference, vector search for AI, and finally, why Big O is basically your budget. We'll start scrappy, intentionally hit some massive scaling bottlenecks, and learn how foundational AI architecture actually solves them.
Let's kick things off with part 1, the chatbot scaling problem. Imagine for a second that you're the CTO of a brand new startup. Your very first task? Building a simple customer service chatbot. Now, it doesn't need to be ChatGPT just yet. It just needs to understand some basic intents, like a user saying hello, asking about pricing, or, requesting a refund. To start out, we take the path of least resistance. We just store these 10 intents in a simple Python list. And honestly, if we only have 10 intents, that's absolutely fine. Searching through an array of 10 items one by one in a simple for loop to find a match takes literally a fraction of a millisecond. It works perfectly.
But here is the critical question. What happens when our startup scales? What happens when we expand globally, add thousands of products, and suddenly our scrappy little system has to search through 1 million different user intents?
Well, here's exactly why our bot just broke. We have a major problem because a basic array or list has a search cost of O of n. In Big O notation, n is just the number of items. This means the computer has to physically check every single item sequentially. Imagine having to look at 1 million flashcards one by one just to find the word refund. It is painfully slow. Your users are now waiting seconds or even minutes for a simple reply. And in tech, that's an eternity.
Which brings us right to part 2, lists versus hash tables.
This scaling bottleneck forces our very first major architectural optimization in the lab today. When we compare our traditional list to a hash table, which you probably know better as a standard Python dictionary, we see a massive, and I mean massive, leap in efficiency. Instead of searching sequentially, card by card, a hash table takes the input, runs it through a mathematical formula, and jumps directly to the exact answer bucket. That average lookup time is O of 1, meaning whether you have 10 items or 10 million, it takes the exact same constant amount of time to find what you need. It's a real game changer.
I really want you to think about this in a real-world context. Why doesn't ChatGPT search billions of words one by one every single time you ask it a question, right? If an advanced AI had to use a linear ON search across its entire training dataset, it would take practically forever to answer a single prompt, and has to rely on vastly more efficient data architectures to retrieve that information instantly.
Okay, moving on to part 3, TensorFlow and fast inference.
So how exactly do advanced systems handle this massive computational scale? Well, let's construct the simplest possible TensorFlow intent classifier. Instead of just searching a list, TensorFlow creates a neural network model that processes data through a specific streamlined flow. You take an input, you pass it through mathematical weights, you generate a prediction, and you map that directly to an intent.
Now, the absolutely crucial point here is the architectural trade-off we're making. We willingly pay a massively expensive upfront computational cost to train the model. We crunch the numbers, we adjust the weights, and we burn through those expensive GPU hours. Why? Specifically so that the actual prediction, what we call the inference, becomes incredibly fast and computationally cheap when the user actually types a message. We're essentially shifting the heavy burden of O of n into the training phase so the end user gets to experience near O of 1 speeds.
Let's move to part 4, breaking the magic AI myth.
It's time to demystify what's actually happening inside that AI black box. When we look under the hood at how a framework like TensorFlow tokenizes and stores our vocabulary, we see something super familiar. That intimidating function tokenizer.fitOnTexts. Well, it isn't doing anything mystical. It literally just creates a dictionary. It maps words to numbers using a hash table with an average lookup cost of O of 1.
And this brilliantly illustrates that AI is not magic. I tell my students this all the time. Every single modern AI system, no matter how ridiculously complex it seems, is fundamentally built upon classic, efficient data structures. We're talking about arrays, matrices, hash tables, trees, graphs, and queues. If you understand these structures, you understand the very DNA of artificial intelligence.
All right, let's look at part 5, vector search for AI.
But what happens when our simple text chatbot evolves? Say it needs to understand complex semantic meaning, not just exact word matches. To do that, it uses embeddings. A simple sentence like "I want a refund" ceases to be just text, it becomes a massive mathematical vector composed of thousands of floating point numbers. Now, imagine a database of millions of these dense vectors. If we try to use our old friend, the linear ON search, to compare the user's vector to millions of stored vectors one by one, that computational cost will absolutely crush our servers.
To solve this, we absolutely must introduce purpose-built infrastructure. This is exactly why vector databases like Pinecone, Weaviate, or Milvus exist in the first place. They use highly specialized indexing structures. Think of it like mapping out data points into a web of closely related neighborhoods to cluster similar vectors together. This specialized architecture reduces the search costs dramatically, making semantic search across millions of dimensions actually feasible in just milliseconds.
Which brings us to our final section, Part 6, Neural Network Cost and Big O Budgeting.
This is where theory meets reality, folks. In a neural network, every single neuron performs continuous mathematical operations. This means that adding more layers to make your AI smarter drastically increases memory usage and computation requirements. You're essentially transforming Big O notation from a theoretical computer science concept right into real-world resource planning. Because every calculation takes power, and in the cloud, power is money.
So, put your CTO hat back on for a second and consider these 3 designs. We've got Design A, a Python list with O of n linear search. Design B, a dictionary with O of 1 hash lookup. And Design C, a TensorFlow model with expensive training but lightning-fast inference. Ask yourself, which architecture would you choose for 50 users? What about 5,000? What about 5 million users? Your choice completely changes based on your scale.
Because here is the brutal truth of software engineering. If you get this architectural choice wrong, your unoptimized search strategy could easily turn a cheap $20 a month prototype into a $20,000 a month disaster the second it hits the public internet. So, the most crucial point we've discovered in the lab today is that algorithmic efficiency isn't just dry mathematics. Big O is your budgeting. It's your cloud spending. It's your response time. It is your scalability. It is literally the language of engineering efficiency.
Ultimately, the next time you open your editor to write a line of code, or the next time you're whiteboarding a system architecture, I want you to remember this final thought from today's explainer. Big O is whether your AI startup survives. So, before you launch your next big project, ask yourself, do you actually know the Big O of your own business model? Thanks for stepping into the lab with me today. Keep building, keep optimizing, and class dismissed.